So it's Monday the 9th of January 2023 and I'm on my way to the University of Leicester first thing in the morning. All over the weekend the James Webb Space Telescope and the Hubble Space Telescope have been observing the planet Uranus for us. Now this is a really exciting moment for us. This is the first time we've turned the telescope at this particular target, so a real test, I would say, of the capabilities of the telescope.
Well, they're working away, so I'm hoping there'll be a nice little show and tell for us.
And my emails have been trickling in, even as I've been walking, telling me that more data is available on the archive for me to go and take a look at. So it's going to be a very busy day. Let's start that going. This is our first glimpse of what the data might actually look like. And as we keep going, longer wavelengths will get better and better. There we go, that is Uranus. And look at the black net there is where we think we were pointing. And actually we've got it pretty much spot on just there. And if I scan down, all of these lines just here, they're real. They are Uranian spectra of ethane and acetylene produced high up in the stratosphere.
Hey Lee. Hi Naomi.
Hey.
There we go.
Hey.
Good morning. I understand it's bright and early there in Seattle. Right, can you see yourselves now on screen?
It's loading.
It's loading.
Yep.
Yes,
Yep.
yes we can.
Okay, so what I will show you is at one of the best wavelengths from MUI that we've been able to get.
What wavelength is it? Look at the spectrum.
This is some of the darkest regions that we're confident about. Wow, you can even see glimpses of the rings in these data. What else do we have? There we go. Even better, the rings around Uranus and some hot spots at the North Pole just there. So this is our first glimpse of the data, and I think we can all be extremely happy with it.
But Lee, it is just fantastic to see this. You know, it's been a long time coming, but you know, every moment of those 25 years that we worked on this has come to fruition with this amazing data set. And I thank you to you and your team for spearheading this and putting the proposal together, the observations, these data. I mean, they're just fabulous. I agree with you. This is going to fundamentally change our understanding of Uranus. And then when we get Neptune data, it's going to be the whole ice giant paradigm is going to shift. So it's just fabulous. So thanks. Thanks.
My name's Heidi Hamill, and I am one of the 6 interdisciplinary scientists for James Webb Space Telescope. I started working on the JWST project before it was JWST, nearly 25 years ago, before it was even a formal NASA project. We called it the Next Generation Space Telescope. And so I became involved in the project because I wanted to be able to use this fantastic asset to study objects within our solar system. And that's challenging because they're bright and they move quickly through the sky. Our planetary objects move. So part of my role with the JWST project for the last 20 plus years has been to ensure it did have the capability to observe bright objects and moving objects. NASA's been exploring the solar system for many decades, since before I was even born. I don't think I can capture every single mission that's launched and explored, but boy, let's talk about some highlights. We started with the moon because we knew that we would be sending astronauts there. We wanted them to be aware of what they were getting into. We also, in the early years, sent spacecraft to Venus, many missions to Mars, starting with the Mariners and then the Viking landers. And we've since sent orbiters and rovers like Sojourner, Spirit, Opportunity, Curiosity, and most recently the Perseverance rover. And even a little helicopter at Mars, Ingenuity. Interestingly, when we've been studying these large worlds like Jupiter and Saturn, we have found that their moons have been just as fascinating as the planet themselves. We had the Uranus flyby in 1986 with the Voyager 2 spacecraft. We had the Neptune flyby with Voyager 2 in 1989. Right now, the outer planets in our solar system, Uranus and Neptune, are the least explored planets in our solar system. One of the things that I had learned in the years since Voyager, when we continued to study Uranus and Neptune with newer ground-based telescopes, and the Hubble Space Telescope after it had its servicing mission.
Hubble threw us a few curves, and I think it's really a testament to the whole team that we were able to overcome them, and that we have a Wide Field Camera 3 in the telescope, which will help to unlock the secrets of the universe.
What I learned was that these planets change. And that what Voyager saw was a snapshot in time, but the planets today don't look like that. I use the analogy that it's like if I showed you a picture of me in 1986, that's not how I look today, right? I've changed. And so using only the Voyager data doesn't give us an accurate understanding of how these planets change with time. And so the need to continue observing them with ever more powerful tools until we get a new mission there, that has only intensified over the years.
Good evening. Welcome to the Space Telescope Science Institute in Baltimore. I'm Don Savage, Public Affairs Officer for NASA's Office of Space Science. This evening, we're pleased to announce the start of a week-long campaign of observations of the impact of periodic comet Shoemaker-Levy 9 with Jupiter. The impact of the first fragment occurred earlier this afternoon at about 3:54, and scientists around the world participating in the NASA National Science Foundation observing campaign, as well as virtually every other telescope and observatory around the world, have been watching.
For the impact of Shoemaker-Levy 9, my team and I were set up in the Institute, Space Telescope Science Institute, and for the actual event of the first impact, we were down in the basement where they had computer screens where the technicians normally check the data to make sure everything's okay. Normally, astronomers are not allowed in there. They don't let people in, but this was a special event. So we were all crowded in there waiting to see the first images. And when the first images came, it was pandemonium. I mean, it was like, what is this? Could this be a moon? Is this a real plume? What is it? Get an almanac. Check where Io is. Yeah,
because we had to reduce the other one a little bit.
that one looks pretty good. The fit. And then when the first image of the impact site came up, we were like, holy smokes. There's video of me like pointing at the screen. Everyone around us is, oh.
Jennifer, yes, look at this. Oh my God. Isn't that incredible? It's right in the methane. That's amazing. That's what we all said. And in the initial orbit, you can see
At that time, there was a little tiny computer monitor up above the big screen showing Jupiter. And we could see the press conference that was happening one floor up in the auditorium. And Gene Shoemaker, Carolyn Shoemaker, and David Levy were sitting there, you know, not knowing that one floor beneath them, everything was happening. And so I said, we have to break in. And they say, this is a formal NASA press conference. You can't break in. I said, we're going up. That's the kind of person I was. So I said, get me a computer printout, like anything. It was like this thermal paper. Do you know what I'm talking about? It was like this black thermal paper. But you could see Jupiter, you could see the black spot on it. And I said, we're going up. And the TV crew was like, she's going up, she's going up. Because I have to show Gene and Carolyn and David this. It's their comet. It's not fair that they didn't know what was happening one floor below.
Included by Asfog and Benz. And I think we may have some up-to-date information from Heidi Hamel.
I'd like to introduce Dr. Heidi Hamel.
Eugene Shoemaker said he would be personally astonished if we saw nothing. Well, or if we didn't see something. Well, he's not going to be astonished. We actually saw some amazing things.
Oh, boy.
We just downloaded the first 2 orbits. In the first orbit, we were able to see a plume on the edge of the planet. In the second orbit, which I have a raw laser printer output, this is as raw as it gets, we can actually see the impact site itself. And I'll remind you, this is for A, the first one, not the brightest one. So we're going to have a really exciting week.
Why be dull and boring about it, right? Let's have some spectacle. Let's have fun with this. That was sort of my whole presentation style for the whole week, because we would have press conferences every day. And like, what are you seeing today? We're like, who knows? You know, it's going to be the big one hitting tomorrow. What is that going to do? Big black eye on Jupiter was my best guess. The impact of Comet Shoemaker-Levy 9 into Jupiter back in 1994 was a game changer. To actually see an explosion taking place on the planet Jupiter with the Hubble Space Telescope and with other ground-based telescopes really changed our perception of how planet-changing some of these large impacts truly were. All of these places that we have visited with spacecraft, we are really limited in what we can do with our ground-based telescopes. But now, with Hubble and now the James Webb Space Telescope, we are getting new views of all of these places to supplement and complement the results we've gotten from these myriad missions to all these worlds.
And we have a fully deployed JWST observatory.
Future-proofing JWST was not a problem, because what we set out to do was so ambitious that even over the quarter century it took to build this thing, we've never built anything to surpass it.
And then when those first images came out, I was like, wow, it's happening.
Along the way, unfolding itself, deploying a mirror 21 feet wide, a sun shield the size of a tennis court, and 250,000 tiny shutters, each one smaller than a grain of sand.
Well, we can look at everything in the solar system that's not too close to the sun, because we have a sunshade, an umbrella, which protects us, but it only protects us if we don't look too close to the sun. So all of the planets move around in the sky rather quickly, but all of them from Mars on outwards sometimes are in the zone where they're far enough from the sun that we can see them. So that tells us when to look and how to look.
The JWST looks in the infrared, which is kind of like looking at heat. You can do cool things by looking at heat instead of looking at light, because you can look through the dust and gas of nebulas and look through into where planets are being born in new solar systems around new stars.
The reason we wanted to use JWST to study objects in our solar system is that we knew this telescope would have fantastic sensitivity. And we also knew that it would have very stable image quality and stable photometric quality. And those are things we look for in astronomy because they allow us to get higher precision on the objects we're studying. Now, in our solar system, we do send spacecraft to some objects, but we don't send spacecraft everywhere. And so the places that we don't send spacecraft to, we need to use telescopes to study. And having access to the best telescope that we were ever able to build, which is what we anticipated JWST would be, that allowed us to dream and plan and think about what we could do with this premier facility in the solar system.
We have two basic capabilities. One is take pictures, and one is stretch out the light of an object into a rainbow to see how bright is it at each different wavelength. So that's really important for us to do the chemical analysis and the physical analysis of what's in the object.
In any public talk I give about JWST, I always start by explaining what spectroscopy is, because I call it JWST's superpower. The spectra are so fabulous that when you get a group of scientists together, you show them the brand new JWST stuff, and what makes the audience gasp is a spectrum. It's so good, so clean. The lines are so beautifully resolved. The sensitivity is so exquisite that you just see molecules.
So we never get to print a picture of a spectrum in the newspaper because it's too abstract for people, but it's the thing that astronomers use to know what's going on inside those things that we find.
As a chemist, I can tell you the spectroscopy is the best part about the James Webb Space Telescope. Yes, we're getting fantastic images, but even the distant galaxies, you know, the hunt for the first galaxies of the universe, they're dependent on the spectra. The images only give you so much information, and without seeing the actual spectra, you can't confirm the distance of an object or, you know, the pristine nature of that object. I'm Stephanie Milam. I'm the JWST Deputy Project Scientist for Planetary Science. I decided to become a scientist when I was actually very young. I grew up in Houston, Texas, and I went on a field trip down to Johnson Space Center when I was about 6 years old. I came home just absolutely elated, and I told my mom, when I grow up, one day I'm going to be an astronaut, I'm going to work for NASA. Pretty much everything I've done since that moment has been to become a scientist and to work at NASA someday. I knew that I wanted, to become a mission specialist, so I needed to pursue a PhD, but at the time I was working in an environmental laboratory, basically washing glassware for a living to get myself through school. And I knew that I couldn't spend the rest of my life doing this. And I asked my advisor, how can I become a chemist and not have to deal with wet chemistry ever again? I never want to see another beaker. She knew I had a passion for astronomy, and she said, have you ever heard of something called astrochemistry? And that was sort of the turning point, and my laboratory went from, a room where I was washing beakers to now the entire universe studying chemistry of the cosmos. If you would have asked me when I was an undergrad in Kansas whether or not I would be working on the largest astrophysics mission NASA's ever had, I would have never imagined it. Never.
The way the program worked for those of us who were interior to the program, as part of accepting that work with NASA, we were given guaranteed time on this new telescope, especially in the first cycle. And so I knew I had 100 hours of guaranteed time that I was planning to use for solar system observations.
Heidi came to me and she said, I really want my time and my projects to go to the solar system community so that they have this data in hand for future cycles and they really see what we can do with JWST.
We reached out to the community members and asked them, what do you think we should be doing with JWST? What would be unique? What would be challenging? And we invited them to send little tiny mini proposals to me and to my team.
And so we had a couple of conversations about what that program would look like. And she wanted to cover the entire solar system with her time that she was allocated. And so we broke up her time to all of the different planets that we can observe with JWST. So Mars on out, near-Earth asteroids, comets, some of the main features of things like the Great Red Spot, Uranus, Neptune, the outer solar system, all these things. We decided that we needed to have a point person for each of these targets. They would have their own science teams, but we needed somebody to be the go-to that would be responsible for making sure the observations were planned and delivered and the data was published. The best part of Heidi's entire GTO program is it's very international. And that just goes to show how international this project is, how international it is for astronomy, for planetary science. We aren't just one small niche group. We aren't 2 or 3 people sitting in a room that are the experts in the field. It takes a whole team. And a lot of that team comes from many different areas and many different backgrounds even. And all of that helps feed in and provide the information that we need to really get a grip on what this data is telling us, learn something about the solar system or the universe in ways that we haven't been able to do.
So one of the things we had to decide as a science working group was how fast really were we going to try to push JWST. After a lot of dialogue, we decided that the orbit of Mars would be the limiting factor. And we looked at how fast Mars moved in the sky. And we said, okay, so that's going to be our target goal for the moving target tracking. That would then be fast enough that it would allow observations of Saturn and Jupiter and Neptune and the Kuiper Belt objects, which all move slower than Mars. NASA had a mission called the DART mission, the Double Asteroid Redirect Test, where they crashed a spacecraft into the moon of an asteroid, and they were looking to see if they could move that moon. Part of the observing we decided to do was try to use JWST to do that. The challenge was that asteroid system with the moon was actually going 3 times faster than the upper limit we had all agreed to in the development of JWST. Huge thanks to the engineers and the operating team for JWST. They were actually able to get the telescope to track fast enough to do that asteroid test, and we did get some fabulous observations with JWST.
So with Webb, we get to see things that we cannot at the present day see from the Earth. Primarily that's because of the Earth's atmosphere. We cannot see through the Earth's atmosphere at some frequencies of light. So what Webb gives us is the ability to go into space and to look at objects that would otherwise we couldn't see at certain wavelengths. And in particular, that's really important for molecular astronomy, which is what I do, which means that we can see the molecules in the atmosphere, tell us information about what the atmospheric composition, temperature, and winds are doing. And basically we're working as a team and trying to decipher the puzzle of Titan's weather. One of the things that we're looking at right now is some of the surface features. Titan has lakes and seas, which are in its northern hemisphere. These are seas of methane, quite unlike the seas that we see on the Earth, but at the same time with some of the same characteristics in terms of rainfall and rivers and shorelines and this sort of stuff. So we're very excited to look at those and see if they're still the same lakes and seas that were seen by Cassini.
You know, we have a lot of stuff going on Mars. We have orbiters and everything. But James Webb can see Mars from the whole side. You can see the whole side of Mars, and you can map it. And this is something that rarely you can do with an instrument like available on James Webb. And that has been amazing because now we can go and look for molecules like methane, which is natural gas, that it could be an indicator of past biology or current biology. That's why we are excited about it. That's what we are working on right now. The same thing we can apply to Europa and Enceladus. And you know, Enceladus is a relatively small moon compared to Mars, but it's like that, waiting to see a little pixel, you know, and something. And then when we point there, we saw a huge plume there. So I mean, when you see those things that, you know, you really get surprised. This cannot be real. So you go back to the data, and then you confirm that there's a big plume coming out of Enceladus.
Some of the data hasn't come yet. I'm still waiting for the Neptune science data. We have a Neptune image that was taken as part of a program to make some beautiful pictures for press releases. And boy, did that whet my appetite for what we will see with the Neptune science.
Even when we were commissioning the telescope, one of our commissioning projects was to look at Jupiter, just so we could study scattered light across the instruments. And within a single minute worth of looking at Jupiter, we already knew that we could detect the rings, the satellites, the great red spot, the aurora, there's haze layers. We saw all of that with 1 minute in commissioning, already knew this was going to be a revolutionary telescope.